Welcome to the intro lecture for Module 4A. As usual, we start this lecture reviewing an engineering disaster. The one today is probably the most infamous one of most engineering disasters that we know of. It is the 9/11 World Trade Center attack. From an engineering perspective, the extreme heat from the resulting fires caused the floors to sag, which in turn led to the perimeter columns buckling and the ultimate collapse of the towers. Note that the steel columns did not melt, as some conspiracy theorists have tried to use in their claims. However, the high temperature significantly reduced the material's yield strength. For example, at 1,000 degrees Fahrenheit, while structural steel does not melt, its yield strength will reduce by more than 50%. As we start to investigate column buckling, consider a typical tensile test. In this type of test, we connect our mechanism to the ends of a slender specimen and pull on both ends. A ductile specimen will neck down near the middle until it ultimately fails by snapping in half. But what would happen if we reversed the load and pushed on the specimen rather than pulling? Eventually, it would bow out near the middle of the specimen. This phenomena is called buckling. Buckling occurs due to part geometry rather than material strength. Buckling occurs suddenly with no warning, thus it is one of the more dangerous modes of failure. To understand buckling failure, we first need to define different types of beam columns. Long columns, as defined by a slenderness ratio, will usually fail by buckling. Short or intermediate columns fail by either crushing or crippling. Central versus eccentric loading refers to a load's position relative to a column's moment of inertia. The analysis method differs when you have eccentric as opposed to centrally loaded columns. Two results are needed to determine whether we have a long, short, or intermediate column. The slenderness ratio considers the geometry of the column, that is, the effective length divided by the radius of gyration. The critical slenderness ratio is based on the material properties. It's pi times the square root of 2 times the modulus of elasticity divided by the compressive yield strength. If the value of the geometric slenderness ratio is greater than the critical slenderness ratio, we are dealing with a long column and need to use the Euler formula for analysis. If the value of the geometric slenderness ratio is less than the critical slenderness ratio, we are dealing with a short or intermediate column and need to use the Johnson formula for analysis. Here are the formulas for slenderness ratio, radius of gyration, and critical slenderness ratio. These graphs explain the reason why we need to compare the geometric and critical slenderness ratios. The graph on the left shows the slenderness ratios compared to the material yield strength. Any points to the right of the curve will result in column failure. The safe areas are to the left of the curve. Recall that the geometric slenderness ratio is based on the effective length of the column. What is the effective length? The way the ends of the columns are constrained affect the slenderness ratio and overall structural performance of the column. The pinned or pinned at both ends scenario is considered the nominal column setup. In the chart, note the column that indicates AISC recommends. AISC is the American Institute of Steel Construction, and these are the values we will use when we do our column analysis. Note the rows for rounded, and pin both have an effective length of 1. The next one is a fixed free column where there is no support at the top, and the effective length is much longer. It's about 2.1. Fixed pinned or fixed fix are much safer designs, and thus the effective length is reduced by either 0.8 or 0.65. The critical load is a theoretical limit beyond which the column will buckle. Likewise, the Euler stress is the limit beyond which long columns will buckle. The factor of safety is found by comparing the Euler stress to the working stress. Another caveat is that the Euler stress must be less than 1/2 of the material's yield strength. Otherwise, failure will not occur within the Euler buckling range, and other methods of analysis will be needed. When the column is considered short or intermediate, the Johnson equation must be used. Factors of safety compare the Johnson load or stress to the applied load or stress. What are the other methods when neither the Euler nor Johnson formulas are applicable? I ran into this once while evaluating a large bridge crane for which the columns were significantly oversized. While I was getting a factor of safety of nearly 20-1 with the Euler method, I realized it was not a reliable calculation. Therefore, I had to use the Rankine method. This method assumes crippling will occur rather than buckling. Remember, buckling occurs when the column bows out at or near the midpoint. Crippling is a different type of failure. Think about when an empty soda can is crushed and it doesn't bend off center, it rather collapses on itself. That's a good definition of crippling. This is the application where I had to use the Rankine method. Note that I still had a factor of safety of 13-1, but now I could feel more confident that the design would perform as intended. So we'll end this video here. In class, we will work through a column buckling problem together. In the next video, we will look at how we need to handle column loads that are not at the center of the column.